Hi all. Today we are going to see question number 31 from Mechanical Paper 2 Gate 2019. So you are given a prismatic straight elastic cantilever beam like this with some uniformly varying load distribution. So you are asked what is the magnitude of the maximum deflection. So you can see if you remember the formula, you can directly just tick the answer. But however, if it's difficult to remember the formula, it's always good to learn the method, how to actually derive this formula. So before going into the solution, you can check out more detail about this particular topic of deflection in beams uh, in the NPTEL lecture Strength of Materials by S.K. Bhattacharya from IIT Kharagpur. In this problem, we will be using double integration method. So in order to use that, we are going to use this basic formula for the deflection of beam. So we are going to solve this differential equation overall by finding what is actually the moment, and finally we'll get what is the maximum deflection from this formula. So let's go ahead. So one important thing to notice here is what is actually your Q. So typically you will have a loading condition like this, which is uniformly varying, right? So which will be decreasing like this, forming a triangle. So you will have a function which will tell that it is let's say Q1 Newton per meter square. So means that is the function which is varying, okay, depending on the length. But here the thing is, what is here Q is actually the magnitude of this particular line, the last line, which is the last force at that point. Okay, so that means you need to find what is this function actually. Okay, so let's see how to find that. So now you are having if you look carefully, you are having one triangle in this sense, and let's see at some distance what is the triangle. Okay, so you're going to have something like this, right? So now here it is Q. So total length, let's assume to be L, which is given as L. So let's say at some x distance, let's consider this as Qx because we don't know what it is. So since you can see that your, let's mark it A, B, A dash, B dash, C. So your ABC and A dash, B dash, C are similar triangles. So they are similar triangles. So what you can write is Q by L is equal to Qx by X. So your function is this actually. So now we can utilize this function to actually solve the problem. So how we'll solve the problem? Let's go ahead and see. So now you are having a cantilever beam like this. So let's consider at some x distance, some point, let's say RB. Okay, so now you are going to have some loading condition like this, which is decreasing, uniformly varying load. Now we know its function, right? So yeah, so this is x. Okay, so now we know its function Qx, which is Qx by L. So what is the moment at B due to that particular loading? So you can write it as, so this is per unit length, right? So you need to multiply its length x. Now like in typical uniformly distributed loads, you will multiply that q into that particular length. But here what are you having is varying load, so you will have only half of it. So if you see here, only half of this thing will be there, so that means you are not going to take QL, instead half QL. So like that you are going to get here x by 2. Okay, now this is the load. Now where will the moment act? What is the moment arm? So this is a triangle, so that means you are going to have it acting at the centroid. So that means if this was total was x, so here it will be x by 3. So your moment arm will be x by 3. Therefore your moment you can write finally as qx cube by 6L. So this is the function of your moment. So now how to use this function? In this problem we are going to use double integration method. So we can write the curvature formula as this, m by ei. So here m is a function of x actually, so you can write this as qx cube by 6 EIL. So now integrating both sides once, you will get dy by dx is equal to qx raised to 4 by 24 EIL plus c1. Okay, again integrate both sides. So integrating both sides, you will get y is equal to q raised to x raised to 5 by 120 EIL, okay, plus c1x plus next constant of integration c2. So now let's use boundary conditions on these two equations. So what are the boundary conditions? So you are having your cantilever beam, and when it deforms under this uniformly varying load, it will have some curvature like this. Okay, from here we are taking x, right? So now at x is equal to L, your y is equal to y dash is equal to 0, both. So let's use the first equation with the condition. So you will get c1 is equal to minus q into, instead of x, L raised to 4 by 24 EIL, which is minus q L cube by 24 EI. Okay, now using the second equation with those condition, you will get c1 into x, so your x is L, plus c2 plus q L raised to 5 by 120 EIL, okay, is equal to 0. So therefore c2 is equal to minus q, this LL will cancel, and you will get this minus c1L. So minus c1L, so c1L is already negative, so you will get here plus, so q L cube into L, so L raised to 4 by 24 EI. Your c2 is equal to qL raised to 4 by EI into, so here 120, and you will get 96. So upon solving this, what you are going to get? Therefore you can write c2 is equal to qL raised to 4 by 30 EI. Now when you see the final equation, you are having c1 is equal to minus qL cube by 24 EI and c2 is equal to QL raised to 4 by 30A. So therefore you can write your y is equal to Qx raised to 5 by 120 EIL plus C1. So that will be minus QL cube by 24 EI into X plus your C2 QL raised to 4 by 30 EI. So now, like I said, if you are having cantilever beam, you will have at this point maximum deflection. So at X is equal to 0, you need to find what is Y. So your Y max is going to be, so now let's check the option. So you can see that option B is the answer. So this was a double integration method that we used to actually solve this problem. There are many other methods you can use to solve this problem. For example, moment area method. So you can refer to this lecture by NPTEL for more details about these methods. So thank you.